I'm loving it. Back to reality. Will we derive gravity? Oh, that was like on February 8th or something like that. But H, Planck's quantum of action. Might we discover something very interesting between it and the golden ratio? Why do I say this? Well, I'm looking at it right here. You all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. Yes, we are back. We took a wee bit of time off. We totally got lazy. We're doing some other things. Did we discover some new interesting things? Perhaps. Could it have been spent better? Most likely. But while I was going through, I was actually looking for the derivation. I know I had done on here at one point a Planck's constant H or H bar. The wee bit of magic we'll get into at the end. And I was searching over my channel. I'm like, I kept finding a video, and I'm like, I went into it. I'm like, oh, I did this as a response video to I think like Demystify Size podcast. They had Professor Unziger on, and actually they had round two with him this past weekend. Interesting stuff. Do I always agree with what everyone says? No, that's fine. That's called sciencing. You're supposed to explore different ideas and make sure you actually touch reality. Why? Because isn't that what science is? We're supposed to find out at least the best approximation to truth that we can. I don't know. I don't know. But hey, welcome Fractal Automata. What's going on? Okay, so let's break it down. Number one, we'll go to our friend again, links in the doobly-doo. Go to our friend Wikipedia, as I actually make sure to share my screen this time. Okay, I'd edited the video that I blathered on for 10 minutes without sharing my screen. I had done it twice and I forgot to re-upload it. I should do that in the morning. But Planck's constant. As opposed to Planck units, which we've been doing before, and I actually created a playlist, so you have a playlist there in case anyone wants to play around with any of the equations or go through any of that jazz there. But the Planck constant, or Planck's constant, is a fundamental physical constant of foundational importance in quantum mechanics. It gives a relationship between the energy of a photon and its frequency by the mass-energy equivalence, the relationship between mass and frequency. Specifically, a photon's energy is equal to its frequency multiplied by the Planck constant. The constant is generally denoted by h. The reduced Planck's constant or Dirac constant equal to that constant divided by 2 pi. Because who doesn't like some pi? And generally noted by h bar. Groovy. And we got all this different jazz, the different connections there. It's absolutely fascinating. We can look into that another time. Okay. So what are we looking for here? According to CoData, Planck's constant H. And this was redefined because before I think they had maybe 10 or 11 significant digits, maybe 12 there, and then they had error bars for like the last two or so. With the update, now we're up to 9 significant digits, and they're cutting off. They're saying we have a high degree of confidence up to this very digit here. What are the digits we're looking for? We're looking for 6.626.07015 times 10 to the negative 34 joule hertz to the negative 1. What the heck is a joules hertz? All right, we go to our friend Wolfram Alpha to break it down. Just type in Planck's constant. Cool. Gives you the options to do either Planck's constant or reduce Planck's constant. So either H or H bar. H, Planck's constant. Got that number there, joule seconds. Different derivations which are useful. As we can see, it's 2 pi times reduced Planck's constant. We get the proton elemental viscosity there, which is also interesting. Okay, basic unit dimensions. The claim is if we use these ingredients here, mass, length squared, and time to the -1, which essentially means we divide by time. If we can utilize a set of coherent units, maybe we can figure out what's going on here. So what are we doing here? Okay, I'm gonna go back to our friend over here. As we note, this is H bar, because that's a little squiggly line through it. Because rather than doing, I suppose, you just throw 2 pi in front of it. And that's essentially what it comes out to be. Okay, so for this, we have our dimensional ingredients, and we're going to utilize the universal binomial factorization equation. What the heck is that thing? Again, it's the method that Thad had developed, and we use at the monastery. So what we do is we have a primary action, and then we multiply it by its boundary conditions, which in this case, what we just got from Wolfram alpha right there. We got our mass, we got our length squared, and times to the -1 means we put time in the denominator. So cool. So we got Planck length squared, Planck mass. We divide that by the Planck time again. We have a playlist. So if anyone wants to utilize any of those things, so as many significant digits as they want, that's the claim. Feel free to use it. So our primary action for this would actually just be a circle. So you've got stuff, the ingredients there, and they do a thing, a primary action. The interesting thing you notice, spending enough time on Wolfram alpha and look at the different constants, right around the 7th-ish significant digit place, things often would seem to get a bit wonky. Now, I'm not saying that's one of the reasons why they may or may not have had to redefine SI to help make sure it was coherent. I'm gonna do it on the internet. A lot of smart people decided that, not me. But basically, that's why we have a terminal action. Some may say it's an error correction, or if you're operating in the realm of geometric objects that happens to be hyperbolic in nature, i.e., the complement of the hyperbolic figure 8 naught, maybe there is some inversion. I know, I believe it was Richard from the Wolfram Institute. He's like, when I think of hyperbolic space, I think of it as like negative space. And I'm like, that sounds crazy. And you start hearing these terms like counter space that have been discussed for a while. It's like, what is that? I'm like, it's kind of like it's going in on itself. So isn't that kind of like effectively a negative space? I mean, I don't know. That kind of sounds like the concept with, I think, like within string theory. It's like we have a compactified dimension. We have no idea how. Okay, so what if it's just our normal realm persist? Just kind of an inversion. Again, that's conjecture. That is conjecture. I am totally biased on this. Should be open and transparent as much as we can. Getting back to this thing without bloviating, we have a primary action in this case. We'll throw a circle there, so 2 pi. We have our dimensional ingredients. It's the stuff we're using to create this magical or computational concoction. We have a terminal action. What is that? The form is 1 plus our terminal action here. So our terminal action, and then we multiply it by the break in scale symmetry. No, excuse me, I'm using the wrong terminology. The inversion boundary. Basically, this little thing here, this boxes, you just basically put 10 to the -7, which coincidentally, where do we get that 10 to the -7? Oh, this is some wizardry right here, my friends. Take the Planck mass, multiply it by the Planck length, and then we divide it by the Planck charge squared. And since we're dividing it, we raise it to -2. We click to make sure it's multiplication, because this seems like a weird thing to ask Wolfram alpha. Okay. Yeah. Okay, so we get that. Planck mass, the Planck length per Planck electric charge squared. This number seems very interesting. What? 1K sub A. Amper's constant. That's very interesting. It's 1 times 10 to the -7 kilogram meters per second squared ampere squared. Huh. That's where we get our 10 to the negative 7 from. So, that's what goes there. In this case, our terminal action is made up of 1 plus 1 over the golden ratio squared. And then we multiply that by J1 and J2 squared. What the heck are J1 and J2? We go to from the hyperbolic vortex equation. So Wolfram alpha, link to it if you want to click on it at all. Okay, that's our 1 over x plus a. It's the t-shirt that I'm wearing right here. It's the 1 over x plus x flux x cubed divided by 2 pi. So you kind of got like a bulk over there. That's divided by a circle. And you set it equal to, okay, that's kind of hard to read. You set it equal to I raised to the I. That's raised to the negative pi divided by 2. So you got like a little twist over there. And then we do need a lambda. When Thad figured out that lambda, it happened to be the magnitude of the Planck mass gap. 2.1764 times 10 to the negative 8. Oh, very interesting. And it gives us 4 answers. So the first answer, again right here, we go, and then we square it. Oh my God, I need a new computer. You can do it. You can do it. You can compute, my friend. Oh, it already did. That was a new error on my part. Okay, we get this number. Wait, what the heck is this number? 0.00729735257, yada yada yada. Okay. It's a very random number, isn't it? Well, we type in the line structure constant. This is something that it's a dimensionless constant. We literally derive it from all of our measurements. And I think we've got it down to a good bit of numbers. Yeah, alpha, the fine structure constant. What's this? 0.00729735257. 729935525. My friends, that appears to be a geometric derivation of the fine structure constant. But that's not why we're here right now. We're going back to our thingy over here. All right, well, wrong screen. Wrong screen. Hey, Fishmo, thank you for joining, my friend. Hey, Six, good to see you. Good to see. It's it. Listen, man, I was never really a math guy, and then it's like, 'cause a lot of time it's like, yeah, I can kind of go through this, but it's kind of a pain in the butt. It kind of feels like I'd rather do other things unless it was interesting. And then I realized, oh, look, we have Wolfram Alpha. It basically does the math for you. You just need to understand a little bit of it. I just view it as wizardry. It's like, all right, you take the stuff, you say some words, you write some magical words in there, and then things happen. I'm like, huh, it's computational wizardry. But that's my claim, and that's how I like to look at it. Okay. Oh, what were we talking? Our J1 and J2. Okay. I went on a tangent. I've never done that before. Okay. It's a hyperbolic vortex. It basically has 4 answers. That first one, the claim is it generates a fine structure constant, all uncontroversial digits, because there is some controversy in there. Some people disagree. It's fine. Second fine structure constant, and then 3 and 4, again, reverse order there. So we take these two numbers, we square them. And that's where they go. So literally, the primary action is a circle there, which we'll see. We have our dimensional ingredients. So we got our stuff. It's doing a circle thing. We multiply by the terminal boundary, which is basically just this little action over here. 1 plus 1 over the golden ratio, times those first 2 answers squared when you sum them, times that break in scale symmetry, the 10 to the negative 7. Cool. Well, that's what we're going for. What the heck do we get? Okay. So let's do this. Okay. So the numbers, we get there. Okay. Just literally just throw it in. Okay. Oh my God, it's a lot of digits and everything. Realistically, I could just literally type those Planck constants in there just as letters, and it's going to give a pretty good approximation. But we want to use about 14 decimal places because I think that's basically was it. I believe Brian Greene, I believe Professor Greene, had said something along the lines of Newton came along and he gave us 7 significant digits to gravity, and Einstein came along and he gave us 7 more. It's like 7 and 7. That's very interesting. I'm just saying. Okay, what do we got here? So we want Planck's constant, not the reduced one. We ninja that circle in there. We got that 2 pi. Groovy. All right. This is the Planck length squared. It's a really small thing. This is the Planck mass multiplied by that. Then we divide by the Planck time. That's 10 to the negative 44 thing over here. All right. So we got our stuff, our dimensional ingredients. They're doing a thing, which is a circle. And then we multiply it by that terminal action. Basically, that little thing where we're claiming there's an inversion there, around 10 to the negative 7, but it's easier to express it just dividing it by 10 to the 7. So that's why it's on the bottom and it's not negative 7. Because it's literally dividing. That's what it's going to do anyway. That's one of the math things that you kind of need to get a little more accustomed to, 6 there. Once you realize that, you're like, okay, this makes it. Because before I'm like, why is this over here? It's making my brain hurt. And now it's like, oh, I can actually kind of do this stuff. Groovy. And again, it's 1 plus, in our numerator here, in the top thing here, it's the golden ratio, 1 over the golden ratio, which you can also express as the golden ratio to 1/2. Again, that's another mathy thingy. We multiply it by, oh, look, those are the 2 answers squared. We add them together. Those are those thingies right there. Cool. Right? So we got our stuff doing its thing. We got that action times 10 to the negative 7. So we're dividing right there. Gives us this number right here. Okay. Let's go to our friends at NIST. So what we're looking for here, we are looking for 6.626. 6.626 070 070 15. We're cutting that off because we're going to say that's exact times 10 to the negative 34 joules hertz to the negative 1. Yes. Yes. What is it? Hold on, we go back. The actual derivation. What's it called? It is joule seconds. There we go. That's a lot easier to say. What are those last 2 numbers? 15. All right. What are we looking for? 14. You are off beams. Yes, I am. Now, why am I not so worried about this? And again, hey, it could be wrong. Could be totally wrong. But at least it's a prediction. The prediction is, if you look at this, we cut this off at 5. So we're at 1, 2, 3. We're at 9 significant digits. I mean, is it because we measured quote unquote the speed of light to 9 significant digits? Just a question. Just a question. The other thing too is when we go over here. Okay. 1, 4. What's the next digit? 5. Oh, then that's an 8. I don't know about you all, but at least when I was in elementary school, I used to get told if it's 5 or above, you round up. I'm just saying that if our equipment only has the ability to go out so far, to calculate so far, if we're going to cut it off at 9 significant digits and be like, we believe the closest number for this last one is a 5. Well, if your next 2 digits are 5 and 8, and your detector is like, is it a 4. It looks like it's closer to a 5. Maybe it would show a 5. Just a claim on my part, but my friends, this appears to be a geometric derivation of Planck's constant h. And if you want h bar, you literally just pull out the pi. Who wants to pull out pi unless you need to do it for actual calculations and stuff? And then we get that, blah blah blah. Yeah, that basically looks like it. I think it's normally they show it as a 5 and Wolfram Alpha to abbreviate there. But groovy. Hey, Gesho. Good to see you. Good to see you, my friend. But that's all we got for right now. Just want to put it out there, and anytime I can include a little bit more anime, like a beam struggle between Goku and Vegeta, why the heck not? Because science is cool. Or at least that's my claim. So, have a nice night, everybody. Take care of yourselves. It's a wacky and wild world out there, but I think some good things are right on the horizon.